Welcome to School of Computing. In today's session, we try to understand AVL trees. As part of today's session, we discuss introduction to AVL tree, the limitations of binary search tree BST, AVL tree rotations, and finally implementation of AVL tree in C programming language. So what is AVL tree? An AVL tree, it's named after its inventors Adelson, Welsky and Landis. It's a self-balancing binary search tree. So the point to be noted here is AVL tree is also a binary search tree. It was the first data structure of its kind designed to prevent the performance degradation that occurs in standard binary search tree. So it's very clear there are limitations in binary search tree, especially when it is skewed or unbalanced. So we try to understand in detail what are the limitations in BST and how AVL tree can help us in overcoming those limitations. So BST is not efficient when it is skewed or unbalanced, and AVL is a height balanced tree which is very effective for search applications. AVL tree uses the concept of balancing factor. So we try to understand in detail what do you mean by balancing factor and how AVL tree ensures the balancing factor. So we will move on, we will try to discuss in detail the limitations of BST, and we also try to understand how AVL tree is constructed, making sure that it is height balanced. So limitations of BST. Now look at these examples. This is a binary search tree. Yes, no doubt it's a binary search tree. Binary search tree is a binary tree with an additional rule that every left child must be less than its parent and parent must be less than right child, and at most two children. So BST is also a binary tree. So look at this binary search tree. 30 is the root node, 15 is the left child and 45 is the right child. Now if you observe the second diagram or the second example, it is also a binary search tree. Second one is also binary search tree, because binary search tree definition, if you observe the definition of binary search tree, at most two children are allowed, maximum two children, and left child must be greater than right child. Left child must be less than the parent and parent must be less than the right child. In this example, there is no right child, but it's okay, still at most two children rule. I can have a node with one child, so it is also a BST, and the last one is also a binary search tree. Now look at these three examples. If you observe, the first tree seems to be little balanced, means there are more or less same number of left childs and right childs. Whereas if you observe the second example, this one, you will find completely the tree inclined towards the left side. There are only left children. There is no right tree at all. Right subtree does not exist. And in the right third example, the right side, you will see only the right children, right subtree exists and the left subtree does not exist. There are no left childs at all. So if you observe second and third trees, they are not balanced, especially with respect to height. One side it is totally zero and the other side there exists a tree or subtree. So such trees are called as skewed. Skewed means it is inclined towards one side. So this is inclined towards the left side. So this is called as left skewed binary tree. Left skewed binary tree or a binary search tree. Similarly, this one is called as right skewed BST. Now, what is the problem with left skewed or the right skewed binary search tree? Now, look at the first example. If I am searching for, let us say, 5, in the first example, if I am searching for 5, I will get 5 in, hardly 3 comparisons. I will compare 5 with 30, does not match, and 5 is less than 30, so I will come to the left side of the tree. 5 and 15 I will compare, 5 is less than 15, so I should see in the left side of 15, and I'll come to the left side of 15 and I'll find 5 here. So in hardly 3 comparisons I came to know that 5 is present in this particular binary search tree. Now for example, if I am searching for an element called as 4, so the key here is 4. If I am searching for 4, what I'll do, I'll compare 4 with 30. It does not match and 4 is less than 30, so I'll come to the left side. 4 is less than 15, again left side. 4 and 5 does not match and 4 is less than 5, so I can expect 4 on the left hand side, but there are no more children, so I conclude that 4 does not exist in this particular BST. This is how we search for a key in a binary search tree. Now, let us observe here. Now, in this left skewed binary search tree, let us say I wanted to search for a data called as 2. So, key is 2. Now, first I will compare 2 with 40. It does not exist, so I will compare 2 with, it does not match and 2 is less than 40, so I will come to left side. I will compare 2 and 30, does not match, and I will compare 2 and 20, then 2 and 10, 2 and 5, 2 and 3, and finally when 2 and 3 are compared, I come to know that 2 is less than 3, does not match, so I should search on the left hand side of 3, but that is the end of the tree. I don't have any more left children to the 3, so I finally conclude like 2 does not exist. So this particular key does not exist in the tree. Now please observe what we have done. In order to come to a conclusion that 2 does not exist, how many comparisons we have made? How many comparisons we have made? We have compared each and every element with 2 and finally concluded like 2 does not exist, which is very much same as linear search. You all know what is a linear search algorithm. So there is no efficiency at all if the tree is left skewed, and if I am searching for 2, what happened? This worked like a linear search. It consumed maximum search operations. So performance of BST is same as linear search when it is skewed. And same is the case in the right skewed tree. For example, here let us assume key is 800. When I will come to know that 800 does not exist after doing maximum comparisons, all n number of comparisons. So again it is same as linear search. So in the beginning of our discussion, we mentioned a point like there are limitations in BST. What are the limitations in BST? BST's performance will be very poor. Performance degradation occurs especially when the binary search tree is skewed tree or unbalanced tree. Skewed can be left skewed or right skewed. So these are the limitations in BST. So I hope you understood the problem with BST. So what is the problem with BST? The problem is BST's performance is same as linear search. So BST does not offer good performance when it is skewed. So what is a skewed tree we have seen? So when it is skewed, the performance is very poor. It is almost same as a linear search algorithm. So how do we overcome this problem? Solution to this problem is solution to this problem is so what is the solution? Solution to this problem is AVL tree. So in the skewed trees we have seen the height of the tree was height from root node, if you calculate, it's very big because the tree was lengthy from root node to the leaf node. If you see, it was inclined totally towards one side, either left side or right side, and it was imbalanced. The left side, in a left skewed tree, left side you have lot of children, right side it is nil, no children at all. Similarly, on the right skewed tree, in a right skewed tree, you find all your nodes only on the right side and left side it is empty. So they are not balanced trees. Skewed trees are not height balanced, and AVL tree is height balanced. So what do you mean by height balanced? Height balanced means for every node we will calculate the height, and height must be between -1 to +1, which is called as balancing factor. So what is balancing factor? It is -1 to +1, means height at a given node can be -1 or 0 or +1. So these are the only three possible values allowed as a height at a given node. And for every node we will calculate the height. If there is a violation of balancing factor, we will apply something called as rotations. We will apply something called as rotations to make the tree as height balanced. So the most important concept in AVL tree is balancing factor and rotations. Balancing factor means height at any node must be either -1 or 0 or +1. Means it's a range -1 to +1. If the height violates the rule of balancing factor, if you get anything less than -1 or anything more than +1, you have to apply rotations to convert that imbalanced tree into a balanced tree. Rotations are of two types. Rotations are of two types: single and double. Single and double. Under single, we have two rotations. One is called as LL rotation. Another one is called as RR rotation. In a double rotation also, we have two types. One is LR, another one is RL. So we try to understand these four types of rotations in detail by taking couple of examples. So let me take one example. For example, I am constructing a tree and the first data element, which the key first data which I wanted to insert is 30. Second data item is 20. Now if I am following a binary search tree rule, the first data item is 30 and the second data item is 20, and 20 should become the left child because of BST rule. So 20 will become the left child. Now how do I know whether this is an AVL tree or not? We need to calculate the height. We need to calculate the height at every node. So how do we calculate height? To calculate the height at a node, the formula is height at a node is calculated as height of the left subtree minus height of the right subtree. Now look at 20. At this particular node, what is the height? So I have only two nodes now. At this particular node 20, what is the height? 20 is the leaf node, and what do you mean by leaf node? It will not have any left child or right child. So there is no left subtree and right subtree. So it will be 0 minus 0 and height at 20. So how do I calculate height at 20? So what do I find on the left hand side of 20? There is no children on left side of 20. There is no children on right side of 20, and hence the height at 20 is 0. So what do you mean by that? Height at leaf node will be always 0. Similarly, how do I calculate height of 30? Height at 30. Now again, height of left subtree minus right subtree. On the left hand side of 30, how many edges we are able to find? There is only one edge. So height on the left hand side is 1. Simply count the number of edges from root node to leaf node, or the current node to the leaf node. So current node is 30. From 30 on the left hand side of 30, from 30 to leaf node, how many edges you are able to see? There is only one edge. So height on the left hand side is 1 minus height on the right hand side of 30. Do I find any right subtree? I don't have a right subtree. So 1 minus 0, height at 30, which is a root node, is 1. Now there is an important point to be noted. There is an important point to be noted here. For example, imagine 30 as a right child, 40 have couple of children left and right. Let us say this is 35 and this is 50. 50 also have one right child, 70. Now in this case, what will be the height at 30? What will be the height at 30? Please observe. Formula is height of left subtree minus height at right subtree. Left side there is only one edge, so it is 1 minus. Now please observe at the right side. From root node or from current node 30, you have to see how many leaf nodes are there. There are 2 leaf nodes. On the left hand side, I had only one leaf node, so I had no confusion. I just saw how many edges are there from 30 to 20. But in right side, in this example, in the right side you have two child leaf nodes, 35 and 70. 35 and 70. So you have to find the height of the right subtree by finding the number of edges from 30 to both its leaf nodes. So from 30 to 35, how many edges we have? From 30 to 35, there are two edges. So max of, now 30 to 35, how many edges are there? Two edges. So let me write it. 2. Then what is the other leaf node? 70. So from 30 to 70, how many edges are there? 1, 2, 30 to 40, 40 to 50, 50 to 70. So how many edges are there? 3 edges are there. So since I have two leaf nodes, I need to find the height from 30 to 35 and from 30 to 70. In both heights, I need to take the maximum value. So what is the maximum of 2 comma 3? 3 is maximum. So I need to do 1 minus max of 2 comma 3 is 3 minus 2 is the height at node 30. So this is the case when you have a tree like this. So when you are calculating height, you should be little careful. You need to see how many leaf nodes are there from your current node, and you need to consider all of them. So I hope how to calculate height at a particular node, that process is clear to you. So we will move on. So let me take the old example. Let me go back with my old example. So this was my previous example where we had only 30 and 20, and height at 20 is 0 because it is leaf node, and height at 30 is 1. Left minus right. Right side I don't have anything, left side it is 1. 1 minus 0, 1. Now look at this tree. Is it balanced or not? Yes. At every node we have calculated the height and it is between -1 to +1. So it is a AVL tree. It is a height balanced AVL tree. This is fine. Now observe carefully. Suppose I wanted to add another element. 30, 20, another element called as 10. Now observe carefully. When I add the third element 10, what is the current status? Now is it still an AVL tree? Is it still a height balanced tree? Let us check it by calculating height at every node. So what is height at node 10? It's a leaf node. So leaf node height will be always 0. No left child and no right child. Height at 20. What is the height at 20? It has one left child and one no right child at all. So it is left minus right. Left side it is 1, right side it is 0. So height at 20 is 1. So height at 10 is 0. Height at 20 it is 1. And what is height at 30? Height at 30 is left minus right. Left side I have two edges, so it is 2 minus right side I don't have anything. So the height at 30 is 2. So do you find an imbalance in this particular tree? Yes, there is an imbalance. Where do you find imbalance? Imbalance is at 30. So is it a balanced tree? Is it AVL tree? No, it is not an AVL tree. There is an imbalance. So imbalance occurred. Yes or no? Imbalance occurred. So when imbalance occurs, what need to be done? What is the solution? So we have to apply rotations. So we have discussed there are 4 types of rotations. What type of rotation need to be applied? So this is a very crucial concept in AVL tree where we have to identify the problem carefully. If you identify the problem carefully, then the proper rotations will be done and properly the tree will be converted into a height balanced tree. So now look at this problem. Where do you find imbalance? Imbalance is at node 13. Now, by looking at the tree from root node, at which side of the tree the problem has occurred? Problem is occurred or found at which side of the tree? Left side or right side? Problem occurred on left side. So I'll write one L. Now, you know very well previously when 10 was not added, when only 30 and 20 were there, was there any problem? Was there any problem? See, when 30 and 20, when only 30 and 20 were there, was there any problem? No, there was no problem and the tree was height balanced. So the problem occurred now because of what? The problem has occurred now because of adding a new node called as 10. Where did the new node got added? On the left child, as a left child or a right child? 10 is a newly added left child. So one more L we will write. So friends, please observe the kind of rotation, whether it is LL, RR, LR or RL, four types of problems we have, rotations need to be done, that is identified based on these two things. So first letter will be based on the problem, based on the side of the problem. Is it the left side or right side? So problem occurred on left side, so first L I have written. Problem occurred due to a left child, so another L. And finally we conclude that it's a LL rotation problem. So when there is a LL rotation, LL comes under what type of rotation? We have seen rotations are of two types, single and double. LL and RR comes under single rotation. So LL comes under single rotation. So what we will do in LL rotation? What do you mean by LL rotation? The meaning is, let me write it here. In LL rotation, problem occurred on left side, and right rotation need to be done. This is an important point, so there should not be any confusion. When I say LL rotation means the problem occurred on left side, so you need to rotate it on the right side to do that height adjustment. So what is the solution? When the problem is LL rotation, what need to be done? You have to do right rotation. Now the point is, where should I do right rotation? You have to do right rotation on imbalanced node. What is your imbalanced node? Imbalanced node is 30. So right node rotation need to be done on 30. So what do you mean by right rotation? So this 30 will be moved to right side. So what will happen when 30 is moved to right side? What will happen? When 30, so this is the existing tree, right? 30, 20, 10. So when I move it to right side, 30 will become the right child, 20 will climb up, and 10, which was at level 2, will come to level 1. So this is what happens after right rotation. Now again calculate the heights. 10 is a leaf node, so height at leaf node is 0. 30 is also a leaf node, height at 30 is 0. 20 is the root node. You have to find the height calculation, you know very well, height of left child minus right child, or left subtree minus right subtree. What is there on the left hand side of 20? Only one edge. What is there on the right side of 20? Only one edge. 1 minus 1, 0. So height at 20 is also 0. Height at every node is in the range of balancing factor minus 1 to plus 1, and hence it is balanced now, right? So this is balanced, this was not balanced. So what we have done, we identified what type of problem it is, and we have done a suitable rotation. So we have seen the example of LL rotation. Let us see the remaining three rotations with similar examples. Let me take another example. So 30 and 40. Suppose if there are only two elements, what will be the height? Let me calculate the height. So first element was 30, so it became root node. Second element was 40, it became the right child. Height at root node, height at leaf node is 0. Now I'll calculate height at 30. You remember the formula for calculating the height. Height of left subtree minus right subtree. Do I have anything on the left side of 30? I don't have anything on left side of 30, so it is 0. Minus what do I find on the right side? Only one edge. So 0 minus 1, 0 minus 1, answer is minus 1. So height at 30 is minus 1, height at 40 is 0. It is perfect, it is AVL tree, it is height balanced. Now, for example, I'll add another element. I'll add another element to this one. 30, 40, then 50. Now again calculate the height. Height at 50 is 0 because it is leaf node. Height at 40, left minus right, left side is nothing. 0, left side of 40 I don't have anything. 0 minus 1, it is minus 1. Similarly, height at 30, left side of 30 I don't have anything, so it is 0 minus right side there are two edges, so it is minus 2. So please note, when I added 50, third element, it created an imbalance. So it is imbalance. When there is an imbalance, what need to be done? We have to do rotations. Before doing rotations, what need to be done? You have to identify the type of the problem. So how do we identify the type of the problem? So two letters we need to write, two alphabets. First alphabet is based on the side where the problem has occurred, whether the problem has occurred on the left side or right side. Problem has occurred on the right side of the tree. So from root node, if you observe, problem has occurred on the right side of the tree. So I write my first alphabet R. And who is responsible for this imbalance? Which newly created element created the imbalance? Because when only 30 and 40 were there, in this case, there was no problem. But when I added 50, it created imbalance. So problem was created because of a left child or right child. 50 is the right child of 40. So problem was created because of right child. So first alphabet will tell which side problem has occurred and because of which child. So second alphabet. So right side I found the problem, and because of a right child it comes under RR rotation. So when there was a LL rotation issue, we have done right rotation, and in RR rotation we have to do a left rotation. So when I do a left rotation means what I'll be doing. How do I do a left rotation? Please observe here, 30, 40, 50. So I'll be doing a left rotation. Where should I do a left rotation? On the imbalanced node. So I'll be doing a left rotation here. So what will happen when I pull down 30? 30 will become the left child. 40 will become the root. 50 will be climbing up from level 2 to level 1. This is after performing left rotation. Again calculate the height. Height at leaf nodes is 0. Height at root node is left minus right, left side 1 edge, right side 1 edge, 1 minus 1, it is 0. Now at every node height is perfectly balanced, it is in the range of -1 to +1, and hence this is balanced tree now. So this is what is right rotation problem, RR problem. In RR problem we do a left rotation. Now similarly we will see the remaining two examples. Now if you remember, rotations are of four types, two types basically, single and double. Under single we have this LL and RR. Means in single we will perform rotation only once. Now LR and RL comes under double rotation. So double rotations. LL, RR we have seen. LR and RL comes under double rotation. What do you mean by that? You need to do rotations twice. Let us try to understand with example. Suppose I have 100 as my first element. Second element is 50. Now when we have only two elements, you know very well that it is height balanced. There is no imbalance and it is fine. Suppose I wanted to add another element. Suppose I wanted to add another element 100, 50, and on the right side of 50 I would like to add another element 75, because 75 is greater than 50, so it will appear on right side. Now let us calculate the height. Height at leaf node is 0, so height at 75 is 0. Height at 50, left minus right. Do I have anything on the left side of 50? Nothing. So 0 minus right side I have one edge. 0 minus 1, it is -1. Similarly, let me calculate height at 100. What is there on the left side of 100? We have two nodes and two edges. So on the left side it is 2 minus. Right side, do I have anything? No, there is no right subtree. 2 minus 0 is 2. So what is the height at 100? It is 2. Is it imbalanced or not? Yes, it is imbalanced, because balancing factor says, what is balancing factor? -1 to +1. Now there is an imbalance at node 100 and I need to resolve this, convert it into a balanced tree. For that I need to identify what type of problem it is. So how do I write my first alphabet, first letter? I need to see which side of the tree the problem has occurred. The problem root node is 100. From root node, if you observe which side the problem has occurred, left side or right side, problem has occurred on the left side of the tree. So first letter is L. Problem has occurred on the left side of the tree. Because of what? Because of what? When 75 was not added, there was no problem. The tree was perfectly balanced. So the problem occurred because of 75. What is 75? Is it a left child or right child? 75 is newly added right child, which created a problem. So problem occurred on the left side of the tree because of right child, and hence the problem comes under LR rotation. The problem comes under LR rotation problem. So what need to be done when we are dealing with LR rotation problem? It comes under double rotation. It comes under double rotation. So what we will do in LR is we have to do two rotations. First one, left rotation should be done. Left rotation must be done on successor of imbalanced node. What is imbalanced node? 100 is the imbalanced node. Successor of 100 is 50. Means you have to do left rotation on successor of imbalanced node. You may get a doubt like, if 100 as a right child, means apart from 50, if I have any other successor, what need to be done? Please note, successor here I refer to the node which comes under that path of imbalance. So 75 is the culprit which actually created the problem. 100 is the imbalance node. In that path, whatever successor of 100 is there, that you have to consider. So, and hence in this example 50 is my successor for 100. So left rotation should be done on 50 and right rotation. So there are two rotations, that's the reason we call it as a double rotation. Right rotation should be done on imbalanced node itself. But remember, right rotation is done on the output of step 1. So there are two steps, this is step 1, step 2. So what is my first step? Do a left rotation. Where should I do a left rotation? I should do a left rotation on 50. So I should do a left rotation on 50. When 50 is further moved to left side, what will happen? 75 will come here and 100 remains like this. So this is the output after step 1. So after doing left rotation on 50, this is what I'll get. This is output of step 1. Now what is step 2? Do a right rotation. Do a right rotation on imbalanced node. What is my imbalanced node? 100. And this is my latest tree, right? On the latest tree I need to perform right rotation on imbalanced node. Means on 100 I will do a right rotation. So this is right rotation on 100. When I do a right rotation on 100, what will happen? 75 will become root, 100 will come to right side because you have done a right rotation, and 50 will climb from level 2 to level 1. So this is step 1. Second, this is step 1 and this is step 2. After performing two stages of rotations, what is my final output? 75 became the root node, 50 and 100 are left and right childs respectively. So is it height balanced? Yes, height at leaf node is 0. Height at leaf node is 0 and here it is 1 minus 1 0. Finally, it became a height balanced tree. So this is an example for your LR rotation. Similarly, we can repeat another example for the final fourth category of rotation called as RL rotation. So for example, I have 30 as my first element, 30, and right side of 30, let us say I have 100. This is the right child. Imagine if there are only two nodes, there will not be any problem. There will not be any problem. It is perfectly balanced. But after 100, let us say one value got inserted which is less than 100 and greater than 30. So let us say 75 got inserted here. This will create a problem. So let us calculate the height at every node. Height at leaf node is 0. Height at 100, left minus right. Left side one edge I have 1 minus right side is 0. 1 minus 0, height at 100 is 1. Height at 30, left minus right. What is there on the left side of 30? Nothing is there. 0 minus how many edges I will get from root to leaf node? There are two edges. So it will be height at 30 is 0 minus 2. It is minus 2. Minus 2 means it is imbalanced. So the problem occurred. It is now imbalanced and I need to perform rotations. So let me identify what type of problem it is. So you know the procedure of identifying. From root node, observe on which side of the tree the problem has occurred. Left side or right side? Right side. Okay, done. Because of which child? 75. Is 75 a left child or right child? It's a left child. And hence the problem is RL rotation problem. So what is RL rotation? First of all, it comes under double rotation. And look at the sequence. What is the first letter? R. So do a right rotation. Do a right rotation. Second letter is L. You will be doing a left rotation. There is no confusion. Where should I do right rotation? Right rotation, step 1. Step 1 will be always done on the successor, as I said. Which successor? That also we have seen. The successor which is actually involved in that process of imbalance. Left rotation should be done on the imbalanced node. And remember, step 2 will be always done on output of step 1. So right rotation on successor. Who is the successor? Imbalanced node is 30, its successor is 100. So I need to do a right rotation on 100. When I do a right rotation on 100, what will happen? 100 will become the right child. 100 will become the right child. 75 will come here and 30 will be as is. So this is the output of step 1. What need to be done? Step 2. Left rotation should be done on imbalanced node. Means left rotation on 30. Left rotation on 30. So when I do a left rotation on 30, what will happen? When I do a left rotation on 30, 30 will become the left child, 75 will become the root, 100 which was at level 2 will climb to level 1. Now what is the height? Height at leaf nodes is 0. Height at 75 is 1 minus 1, 0. It is perfectly balanced. So this is an example of RL rotation. So for any given sequence of numbers, when we construct an AVL tree, we will be applying these kind of rotations. Left rotation, right rotation, means you need to see what type of problem it is. LL, RR, both come under single rotation. LR, RL come under double rotation. So this is what you need to implement these 4 rotations accordingly in order to construct an AVL tree. So what is the advantage of making a tree as a height balanced tree? When the height is balanced and if the balancing factor -1 to +1 is maintained, what we can do is we can avoid that skevedness in the tree and searching becomes efficient and effective. So AVL trees are very good for search applications because they are height balanced trees. So before we move on, before we wind up, let us take another example, a simple sequence of some numbers, and we construct an AVL tree now. So the sequence of numbers are 10. What is the example? Let me take an example. Suppose the numbers are 10, 20, 30, 40, 50, 25. So what is the first element? 10. So you need to calculate height at every new insertion. You need to calculate the height, and if there is an imbalance, you are going to handle it. So only one node, so there is no question of imbalance. Then 20 gets added. What is the height at 20? Leaf node, it is 0. And here it is left minus right. Left side nothing I have, 0, 0 minus 1, it is -1. So when two elements 10 and 20 are inserted, there is no imbalance, this is fine. Next step I'll add 30. So when I add 30, what will happen? 10, 20, 30. Is it creating an imbalance? Let me check. Height at leaf node is 0. Height at 20. Left minus right. Left side nothing I have. Left side of 20 is empty. 0 minus 1, it is minus 1. Similarly it is minus 2 because left side of 10 I have nothing. 0 minus right side I have 2 edges. So there is an imbalance. And what type of problem it is? Problem occurred on the right side because of a right child. RR problem. What is the solution? Do a left rotation. It is a RR means a single rotation, right? Do a single rotation on the imbalanced node. So when I do a single rotation on the imbalanced node, what will happen? 10 will come down, so 20 becomes the root, 10 will come here, 30 will be the right child. So now it is again calculate the heights, it is perfectly balanced, right? All are 0, heights at every node is 0. Let me insert 40 now. So when I insert 40, will it create a problem? Let me check. So height at leaf node, is 0. Height at leaf node 10 is also leaf node. So height at 10 is 0. Height at 30, left minus right. Do I have a left child for 30? I don't have a left child for 30. So left minus right, it is minus 1. Similarly, height at 20, left side I have one edge, 1 minus, right side there are two edges, 1 minus 2, it is again minus 1. So height at every node, if you observe, it is minus 1, 0 and 0. So there is no imbalance. This is also fine. Now let me check what will happen when I add 50. So 20, 10 is on the left side, 30, there is no imbalance as of now. Now when I add 50, will it create a problem? Let me check. So till this point it is fine, there is no imbalance. Let us calculate height at every node again. Height at 50, it's a leaf node 0. Height at 10 is also 0. Height at 40, left minus right, 0 minus 1, it is minus 1. Height at 30, left side of 30 I don't have anything, 0 minus 2, height at 30 is minus 2. And height at 20, left side of 20 I have one child and one edge, so it will be 1 minus, right side see the height, there are 3 edges, 1 minus 3, it is also minus 2. So you find imbalance here, and imbalance is found at two nodes, both at 20 and 30. So how do I solve this problem? First of all, let me identify what type of problem it is. Problem occurred on the right side of the tree, and problem occurred because of 50, which is a right child. So it is basically an RR problem. Now when there is an RR problem, what we will do? We will do a left rotation. Now the point is, where should I do left rotation? Previously we used to do left rotation on the imbalanced node, but here we have two imbalanced nodes, 20 and 30. So please observe, you need to look at the tree from bottom to top. So if the problem occurred at 30, because of which the problem got penetrated or propagated to 20. So first of all, if I resolve the problem here, automatically it may be resolved at 20. So first of all, I need to treat this one. So I'll be doing left rotation on 30. So when I do a left rotation on 30, what will happen? So I need to do a left rotation on 30. So I'll be doing a left rotation on 30. So what will happen? Please focus only on this part of the tree, only this portion, because we are doing a left rotation on this part. So what will happen when we do a left rotation? 30 will come down, 40 will become the right child. It will look like this. 40. Now this portion is done. Now on top of this, again I have as usual 20 and its left child 10. So this is the output after performing left rotation. Now is it height balanced or not? I need to check again. So height at leaf node 0, 0, 0. Height at 41 minus 1, it is 0. Height at 20, 1 minus 1 minus, there are two leaf nodes. 20 to 30 the number of edges are 2. 20 to 50 also number of edges are 2. So maximum you have to take, in any case it is 2. 1 minus 2, it is minus 1. Now the tree is balanced. I don't have any problem now. But we wanted to add another element. What is that another element? 25. So this is as of now perfect. It is balanced. So let me add 25. So where should I add 25? 10 is the left child of 20. And right side there is a 40. And on 40's left and right I have 30 and 50. And as of now the tree is balanced. Now let me add 25. I'll check what will happen. So find the height at leaf nodes 0, 0, 0. Height at 30, left minus right. Left side is 1 edge, right side I don't have anything. 1 minus 0, it is 1. Height at 40. 40's left side, if you observe, there are two edges. 40 to 30, 30 to 25. 2 minus, right side there is 1 edge. 2 minus 1, it is 1. Fine. Till now everything seems to be fine. Let me calculate height at 20. Let me calculate height at 20. Left minus right. Left side we have only 1 edge. So it is 1 minus. Now right side, how many leaf nodes we have on the right side of 20? 25 is one leaf node. 50 is another leaf node. So what I need to do? Max of. Now 20 to 25, what is the height? 20 to 40, 1 edge. 40 to 30, 2 edges. 30 to 25. So from 20 to 25, if I travel, I will be visiting 3 edges. So height is 3, comma. 20 to 50, it is only 2. So what I have to take? I have to take maximum of it. So it will become 1 minus, what is the maximum? 3. 1 minus 3 is minus 2. So height at 20 is minus 2 and it is imbalance. So now tell me why there is an imbalance. There is an imbalance because we added a new element. So imbalance means we need to solve it. So first of all, let us identify what type of problem it is. Does problem occurred on the left side of root node or right side of root node? Problem occurred on the right side of 20. So first letter is R. Second letter is problem occurred because of which child? Left child or right child? 25 is the left child of 30. So hence it comes under RL problem. And you know very well, when there is an RL problem, what need to be done. So this is RL problem and I need to do 2 rotations. RL comes under double rotation. So RL problem, I will be doing 2 rotations. One is right rotation on the successor and left rotation on the imbalanced node. Now look at this particular tree. Now the problem occurred because of whom? The problem has occurred because of 25. Right? Now I need to do a right rotation on this particular imbalanced node. Imbalanced node is 20. I will be doing a left rotation on it. So I need to do a right rotation on the successor. So who is the successor? 40 is the successor. Do a right rotation. When you do a right rotation, what will happen? So 30 will come here because 40 is being shifted right. So 40, then 50. 25 will climb. So this is the output of right rotation. Now 20 as is, it will exist as it is, and 10. This is output of step 1. Now on this output do a left rotation. Now when I do a left rotation, I'll be doing it on the imbalanced node, means I should do it on 20. When I do a left rotation on 20, what will happen? When I do a left rotation on 20, already there is a left child, no? So 20 will come down, 30 will become the root node, 20 will come down, 10 will further go down, 30's right child is 40, 30's right child is 40, 40's right child is 50. Now when we are, please observe this portion of the tree. When we are doing a left rotation on 20, 30 will be promoted as root. When 30 is promoted as root, its right childs will remain in the right side, there is no problem. But 30 has a left child called as 25. Where that 25 will go? As per the binary search tree rule, 25 should be on the right side of 20, and hence 25 will be written here. So finally the tree is constructed like this. Let us calculate the height at every node. Height at leaf node 0, leaf node 0, leaf node 0. Height at 20, 1 minus 1, it is 0. Height at 40, left minus right, left side I don't have anything, 0 minus 1, it is minus 1. And height at 30, left minus right, left side, on 30's left side, whether you go to 30 from 10, whether you go from 30 to 10 or 30 to 25, the number of edges are 2 only. So 2 minus right side, number of edges on right side of 30 is 2. So 2 minus 2, it is 0. So if you observe at every node, the height is either 0 or minus 1, and finally the tree is constructed as a perfectly height balanced AVL tree. So if I construct this one as a regular BST, it will not offer me a great performance when I do a search operation, and if it is a height balanced tree, the search operation will be very effective and efficient. So I hope you understood construction of AVL tree and its benefits when compared with BST, and in the next session we will try to implement AVL tree. In the next session we try to implement AVL tree in C programming language. So quickly if I summarize, BST quickly if I summarize, BST is not efficient when it is skeeved, and AVL is a height balanced tree and it addresses the problems of BST. So in our next session we try to implement all these things, means how do we do a left rotation, right rotation, how do we find the height of a particular node. So entire implementation of AVL tree will be discussed in the next session using C programming language. So I hope you understood the limitations of BST and also how the problems of BST are addressed using AVL tree. Thank you.